clinicians appear to be very comfortable with GitHub apps. It's not a calculator. It's just an enormous risk matrix that be put into the electronic medical record or on a phone app and tell you, given this and this and this and this and this and this history and whatever, here's the recommended guideline, and then if you push a button, here's why, here's the risk, and then if you push another button, and here's the educational note. And that is very different than the old way, which was you get this test result, here's what you do. The test result sort of disappears and the inside disappears, and a simplified recommendation comes out. This is considered a loss of locus control for clinicians, but the young ones seem to be used to it because there's so much information now that they realize they can't carry it all around in their head. So, we're just one voice at the table once we get to disseminate by learning. We may think that we understand risk better than other people. We're just one voice. We need to be much better discussing risk, the social aspects of risk tolerance, decisions about risk, and as we do that, we're being just kinds of voices that are ignored. So we spend a lot of time trying to learn how to explain what we do without crossing the line, pretending in any way that it's hard to put messages on. One society may tolerate a certain trade-off between a few cancers and efficiency, or can't afford to not. Whereas in the United States, we're very risk intolerant and maybe a lot lower in terms of other things. I wanted to finish with a sense of the future and then try to get interactive. I'm much more comfortable talking to people than I am talking to them. So I welcome any discussion here or in the future by email or whatever. Say we really, really want to get rid of it. We weren't just saying we wanted to or discussing it, but it was absolutely imperative to us to get rid of it. There are faster ways than what we're doing. And I want to give credit to Doug. Ted Lowry is a humble and interesting scientist, and I'm really incredibly grateful to call my friend over many, many years. And I'm sure that he agrees that the real high impact is dropping incidence mortality so not just having the promise to go out and advancing fundamental understanding of muscle cancer. Those are what we really want to do. And what we're going to do is as fast as possible. And so instead of this model where we prove that a vaccine works, which is currently a 2-dose prophylactic vaccine that we don't invent, and give it before it starts, and then wait all those years for cancer to be invariably prevented, and then screen people, which is very difficult, several times every 3 years or whatever. There's a theory coming, HPV professor, popularized by Dr. Fox in Nature Reviews, in which we take what Amy Kramer and Alexander Time are doing right now, which is a trial of one dose vaccine. One dose of HPV vaccine lasts at least 5 to 7 years. And if you didn't consider this epidemic of HPV acquisition as any kind of epidemic, and if you could campaign, and if you just give it to everybody, one shot, I'm thinking back to all the time I spent in Africa, to Ibadan, to places that I couldn't even see across the street where Julie and I were kind of across the street together, lost each other in the crowd. You know, if you really want to go to a place where I was just in Addis Ababa, and I was looking around saying, programs are going to be really hard to do here. We need campaigns, something where you go around and do something once. And that means it's successful in very quick places to do it. So, if we combine one dose vaccine and know that it'll last 5 to 7 years at least, we don't know how long it'll last, and that's the big trial that we're doing now to make sure we're right. But while that is being confirmed, so that's the education to do that trial, is if we start planning for a screening of everybody that overlaps that HPV vaccination of the entire epidemic curve, that's in place for faster, which means you wipe out the first. Don't get benefit of those who have active infection at that moment. Certain people can pick up on certain things and screening tests and take advantage of them. If you can motivate donors and give donors to get excited about the notion of doing something definitive about one of the worst cancers, like one of the leading cancers in the world, emerging cancer, in lots of very poor places. It really energize the donor community if they think they can actually put something out rather than just institute a program after last decade. And that's the vision. The vision is to now put screening tests and HPV vaccinations together, and then to start seriously taking a very, very common infection leading to a common cancer and eliminating it or at least controlling it severely. And that's sort of what we're working on now. That's sort of the vision. So, in the end, it's all about people. I want to thank Dr. Cummings for creating these. I sincerely believe it's fun. It's no credit for it, but it's incredibly thousands and thousands of things that he's responsible for. Tony Channing, moving in the direction of the whole world of genetics. And I want to really thank Peggy and Mark Green in particular, because it turns out that everything comes together. Mark was the first one with Peggy to realize that when I was coming in epidemiology, talking about absolute risk or positive predictive value, that the same potential. That when they were studying rare family syndromic clinical genetics, what they were pointing out places in cascades, growth or growth control pathways, which are really hard to find if you just go if you just go and just try to find them, you can't figure and cut into it. They were pointing out entire pathways, each family, each syndromic thing was now leading to an exome kind of exploration of the whole spectrum of that mutation, that critical point of growth, and what it does, and how it's modified, and how this whole, with people with lesser risk, the tip of the iceberg to discover critical points that lead to carcinogenesis. And I think we had a common vision that we wanted to study strong effects, and we wanted to study things that have clinical impact. And their understanding my desire to move into the clinical genetics branch, study HPV, to some site visits to completing and even intervention or age tests that they saw in the field. And I want to especially thank them for enabling the second part number. Thank you very much for that presentation. We have microphones in the aisles. I encourage you to step up and ask questions. We're available here for bits to try to answer. Or challenges. I love you know, sometimes I think we don't argue enough anymore. We're afraid of criticized feelings. But in the grand British tradition, it's just good science to argue about things. It's not personal. Yeah, if someone who did hereditary pathology back in the 80s, we had the psychology, the absolute things, and more prices to the defense system. But I think what you're looking at isn't necessarily specific to the service. We have the same problem as I learned further on with thyroid psychology, whereas in particular, a follicular thyroid cancer is a very difficult entity to classify, which is also perhaps the same thing that treatment you here with the service and the medical lab. The medical system was a tremendous advance. But it's just on the road to recognizing that the real action of the molecular level. And so even with the medical system, eventually deals to say microscopic diagnosis of a molecular process, and the best way to look at molecular process is molecular. So I think more and more we just have to do the first thing with reproducibility. That the best experts in the world are absolutely certain that the experts in their area and confirm. And when they disagree, they can't just say, well, whatever. There's participating response, especially about the reality. And if you look at the whole of Scientology or Scientology, the final second controversy, the invention of organization, because of that, I think it's useful. So that's the type of trust, really. With humility and cooperation with your colleagues, and a sense of humor, like Bob Brennan had, process, because we'll get this all, challenge experts around the world. So we need those people who want to create truth, try to get epidemiologists, but all of us have a day where we all are modeling one big set. We don't know what we're doing, but no one has to believe. The face of the particular customer of the thyroid psychology, I think it's interesting. So I'm thinking about preventing cancer. That's what this is about. It's carrying forward, which is the work of Ian Graham and Alan Hillenstein, which is a very large red micron service on the last age. And then doing that last 5-7 years of protection and that's ongoing now in collaboration with the Gates Foundation. My guess is from our preliminary data, yes, absolutely, we're going to find they are good for the kind of strategy we talk about. Not for lifelong immunity, plenty long enough to wipe out an epidemic of HIV and reduce it to a less common infection. So you think you might not be functioning yet, except you're saying it's like 7 years of recovery from lifetime durability, might not even 10 to 20 years durability if you're only going without trying to crush cervical cancer. Now, we haven't talked about cancer and we haven't talked about a lot of other things, but for the purpose of getting rid of cervical cancer as soon as possible, I'm sure that we can do it with a campaign and about 5 to 7 years of durability. So things for Iran from this ovarian cancer, is it also true for HPV-induced oral cancer? Oral cancer is a whole other topic. Samuel's here, or someone else, expert out. Because different epidemiology, we learned a great deal about the differences. It might be a different story, so I'm not saying that. Thank you. I want to thank everyone for coming today. I encourage you to come over to the library. We're going to have a reception immediately after. You can say hello to all of our speakers and ask additional questions there. Thank you. my pleasure to introduce today's speaker, Suzanne Walker. Suzanne is a professor of microbiology and immunobiology at Harvard Medical School and an affiliate of the Department of Chemistry and Chemical Biology at Harvard University. After receiving a BA in English Literature at the University of Chicago and a PhD in organic chemistry at Princeton, she joined the faculty at Princeton as an instructor of chemistry in 1995. She was promoted to associate professor in 2001 and became the first woman to achieve the rank of full professor of chemistry at Princeton in 2003. She joined the faculty of Harvard Medical School in 2004 and is currently director of the Harvard University Chemical Biology PhD program and an associate editor of the Journal of the American Chemical Society. Dr. Walker is known for her work on bacterial cell envelope biosynthesis. She is an expert on antibiotic mechanism of action and has pioneered approaches to discover and characterize new antibiotic targets and compounds. She also has an interest in glycosyl transferases, including OGG. Her research is characterized by the creative integration of chemistry and biology. Dr. Walker has received numerous awards, including an Alfred P. Sloan Foundation Fellowship, Camille Dreyfus Teacher Scholar Award, the Emil Thomas Kaiser Award in Proven Chemistry, and an Arthur C. Cope Scholar Award. She has also been honored with numerous distinguished lectureships. Of all of her professional achievements, she says she is most proud of being a mentor for many students, both past and present. Please join me in welcoming Suzanne to the NIH.
Thank you, and I'm very honored to be invited to give this lecture. I'm going to tell you about the work that we've done today on glucan transferase, which is not a bacterial enzyme, although our interest in started with the interest in a structurally related bacterial enzyme. And I'm going to focus primarily on the chemistry of this enzyme, because it catalyzes at least 3 distinct chemical transformations using the same active site, 2 of which are known to be physiologically relevant, and the third may well be, but I think at least you're teaching us about a class of reactions that we should think about that may happen in eukaryotic cells. I will also tell you about some recent work that we've done on a class of OGG inhibitors. I started working on OGG a long time ago because it was obvious to me, even then, that OGG is a really important enzyme. I'm putting up some facts on this slide. Observations that other people have made. Most recently, people have found that if you do a large-scale analysis of over 60,000 human genomes, there are no loss-of-function variants in OGG, so it appears to be very constrained in terms of evolution. There are also few missense mutations, and so it's essential in mammals. It's shown to be essential in dividing mammalian cells in cell culture. It's essential for development. If you knock it out, you get embryonic lethality, and if you knock it out in certain cell types, it causes all kinds of problems, and so it's been knocked out of sensory neurons, and mice with that defect are born with very few nerve endings in their skin, and by the age of 6 months of age, they have no nerve endings. It causes motor neuron loss if you knock it out of Schwann cells, so it seems that it affects a whole range of processes, and so understanding its biology is going to be very important, and our role, at least initially, has been to help develop some of the chemical understanding of the enzyme that will enable that. Now, OGG catalyzes a unique type of glycosylation. It was first discovered by Gerald Hart in the 1980s, and the Hart group, the John Hopkins and Hanover's group here at the NIH, did virtually all of the early work on OGG, extending through the 90s. And what makes this reaction that it catalyzes unusual is not the reaction per se. The reaction itself is the transfer of glucan to a serine and threonine hydroxyl on a protein to give you a beta-glucan linkage. And so it's a very equally standard reaction. But what makes it unusual is that the localization of OGG is such that this reaction occurs in the cytoplasm and the nucleus, and most glycosylation events Okay, I'll try to press it harder again. So with the population, eukaryotic cells happens in the hierarchical compartment, and so it was a pretty unusual observation that you got to have a lot of cytoplasmic population, and I think there was a lot of resistance to believing that it was real initially. But Hopkins and Hanover thought that battle for a long time, and there are now enormous numbers of groups working on OGG. So the other thing that makes it unusual is there is an O-glucanase. There's an enzyme that removes the O-glucan modification, and so you get it, and it happens on a time scale that can be fast relative to the half-life of the protein, and so you have a dynamic cycling event, and that kind of behavior is more analogous to post-translational modifications that are involved in, say, cell signaling than it is to a conventional population. So what does OGG do? Well, people still don't really know. It does a wide range of things. One of the initial observations that was made about O-glucanylation is that it's sensitive to glucose levels. And so if you have high glucose levels in cells, or just as glucose comes into the cell, some amounts get shunted into the recognized that glucosination has been linked to diabetic complications and to other problems, and has recently gotten a lot of attention in the cancer field because cancer cells take up a lot of glucose, and you can notice that cancer cells often will overexpress OGT, and that you have high levels of O-GlutMAC that seem to be important for them to survive. So it's possible that OGT could be a therapeutic target, although as you will see, one would have to think very carefully about how to actually inhibit it in a way that isn't lethal. Now, O-GlutMAcylation affects many cellular processes. It's been linked to kinase signaling. These are only a few of them. To protein stability, to transcription. It plays a big role in that. And because there are so many different kinds of substrates in cells, it's hard to dissect its biological function. But there are also other reactions that we now know that it does, which make the story even more complicated. So when I got interested in OGT, it was around the year 2000, and I decided that we could maybe contribute by starting to develop some of the chemical things that you need to really make headway in understanding an important enzyme, and so starting with an OGT structure and proceeding to small molecule inhibitors. And so that work was started by Zen Groves at Princeton and then continued by a series of people at Harvard. Now, OGT resembles, it belongs to a superfamily of glycosyltransferases called the GTP superfamily. They catalyze glycosylations in a metal ion independent manner, and you'll see how they do that in a bit. OGT was predicted to belong to the GTP superfamily, which I have been studying, and it contains the characteristic NMC terminal lobes of that family, but it also contains some features that are not found in any other glycosyltransferases. One of them is this long, you can't tell me that it's long, but there is a long stretch of amino acids that intervenes between the NMC terminal domains, and there's sort of a tetracyclopeptide-rich N-terminal segments. And so these are 34 amino acid helical keratins, which are typically associated with protein-protein interactions, and in fact the TTRs in OGT play a major role in the substrate selection, and so part of the answer to how it chooses its substrates rests not in features of the catalytic domain, but in the TTR domain. And so John Hanover did a lot of the early work of making headway understanding the TTRs. So as I mentioned, we set out to get a crystal structure of OGT, and it was really hard, and so we've been cranking away at it, and this structure of the TTR domain came out of Hanover's lab in a collaboration with Elena Conti, or vice versa, but, and you're looking down the lumen of the TTR, OGT TTR domain, and it forms this beautiful superhelix, and you can see that there's a space in the middle, and so it plays a role in substrate selection, and so one idea was that it combined substrates into that lumen, and Hanover and Conti identified an asparagine ladder that looked like it was involved in combining substrates, which turned out to be a correct hypothesis. It took a number of years more before we were finally able to get the catalytic domain, and it's shown on this slide. And so you can see, the trick to getting it was to actually find a construct of the right length. And so we found, by doing an awful lot of solutions, my graduates in my lab, finally found one that crystallized. And so the structure shown here, you can see the TTRs winding around the top of the active site. The catalytic lobes are in blue and orange, and this has a classic Rossmann fold. And so this, you just can't see it. And the intervening domain passes up against the C-terminal domain. That is a very basic domain. We still don't know what its function is in OGT, so there's a lot of unanswered questions about this protein. Now, if you look at this structure, you can see this purple space filling view of UDP, and lying right over it is a peptide. We crystallize this with UDP in a peptide substrate called the CK2 peptide. And with this structure and with the Conti-Hanover structure, which contained 11 TPRs, we can build a full structural model of OGT because we can superimpose some of these TPRs. And so in looking at it, you can kind of guess why it might have been hard to crystallize. It just has a shape where packing, there's almost no way to imagine packing it that would be possible. So if you're looking down from the TPRs into the active site, you can see the peptide of the CK2 peptide that we crystallized lying right over the UDP, and right here is the cavity where GlutMAC would be if it were present in this structure. And one of the things I liked about this peptide is that it has 4 serines and threonines in it, but only one of them is glycosylated, and that one is pointing right into the active site where you'd expect it to be, and if it were a relevant structure. And so that was a nice feature. In looking at this structure, we could sort of tell that this enzyme has to work by having an ordered mechanism where the UDP GlutMAC binds first, and then the peptide comes on top of it, because the UDP GlutMAC actually creates a binding interface for the peptide. And also you wouldn't be able to get this in if you had this binding there. And so we showed that it binds in an ordered mechanism, and that was important because we wanted to sort of understand the catalytic cycle and be able to get crystal structures of different complexes that would allow us to get a better picture of catalysis, which is really important if you want to go into cells and try to separate function. And so the significance of studying an enzyme in detail is really that it allows you to then design better biological experiments, in my opinion. So this is the reaction cycle for OGT, where it binds UDP GlutMAC first, peptide or protein substrate comes on, there's a reaction, the glycopeptide is released, and then the UDP is released. And so the structure that we first obtained was actually a peptide binding over UDP, which is not on the reaction cycle. And so we wanted to get this ternary substrate complex and the ternary product complex, which can be hard to do. But we were able to get a product complex by allowing the substrate to actually react during crystallization. And you can see from the electron density here that this is a pretty nice structure. And so you can see the sugar bound down into, deeply buried in the pocket, with the only exposed position being this TCU and acetyl group, which turned out to be lucky for us, for reasons that you'll see in a bit. Now, getting the ternary substrate complex is a little bit more difficult because you have to find a way to prevent the substrates from reacting, and you can do that by mutating the protein. What we chose to do was